It is time to summarize our course and tell you a little bit more about this field of sparse representations. If we are to encapsulate the origin of this course into one sentence, it would be this. Given an underdetermined linear system of equations, we are interested in finding its sparsest solution. This is an interesting twist over the classic knowledge in linear algebra, and one that opens up a new chapter in this field. We define the above goal as the problem P0. The L0 norm appearing in the above expression is our notation for an operator that counts the number of non-zeros in X. So the problem posed is exactly this. Find the sparsest solution to the linear system AX equals B. In fact, P0 itself was only the first and intermediate step in our journey. We decided to generalize it and introduce the problem we called P0 epsilon. This newly defined goal is a relaxed version of P0, where AX is no longer required to be exactly equal to B, but rather be epsilon close to it. We justified this change by the desire to have a problem that tends to sparser solutions and provides more robustness to perturbations in A or B. And then it appeared as if we got stuck. We discovered that P0 and its relaxed version P0 epsilon are both too complicated to solve. In fact, in computer science terminology, we can say that these two problems are known to be NP-hard. The reason for this complexity is the exponential number of possible supports that the solution may take. Had we hit an unbreakable barrier? Definitely not. We turned to approximation algorithms that suggest a solution to P0 epsilon while employing a reasonable amount of calculations. We met two breeds of such techniques, greedy and relaxation methods, and described in details how they operate. Far more surprising, and the climax of this course, was the fact that we were able to derive theoretical guarantees for the success of these methods under some conditions. Let's say a few words on the theory we developed. The problem that we resolved is this. Given a matrix A and a sparse vector X, assume that we generate B as A times X plus an epsilon bounded noise. Then we plug A, B, and epsilon into the definition of P0 epsilon and aim to solve it somehow. Our study led us to several interesting findings. First, for epsilon equals to 0, which gets us back to the problem P0, we saw that if X is indeed sparse enough, then it is necessarily the sparsest. Furthermore, the test for optimality was shown to be very easy, relying on the spark or the mutual coherence. A second result of similar flavor was about the stability of P0 epsilon. It stated that if one could solve this problem, its outcome could not be too far from the original X that generated B, and this would be true as long as X is sparse enough. The third and most impressive result referred to the approximation algorithms we proposed, the OMP, the thresholding, and the basis pursuit. We were able to show that all behave very well, guaranteeing either a perfect recovery of the support of X or a solution not far from it. So the bottom line to all of our achievements is that the P0 epsilon problem is a well-defined and well-behaved problem, and solving it in reasonable time is doable. Isn't this great? Well, while it sounds like a lovely theoretical achievement, the question you are probably asking yourself now is, why should we care? What is the point to all this discussion beyond being a nice mathematical riddle? The answer to these questions is very clear and very deep. P0 epsilon and its solution are far more than just a mathematical exercise. All the discussion we covered has immediate consequences to actual signal and image processing and machine learning tasks. This means that everything we described has a profound impact on these fields with very practical implications. Indeed, this is why we are offering a sequel to this course, as we have so much more to tell you. We started this course by briefly explaining the role of models for data processing, and we should widen this discussion. We would like to show you how sparsity and redundancy become key in such modeling of information. We plan to show you how P0 epsilon becomes central in series of tasks and applications and demonstrate how it leads to state-of-the-art results in practically everything it touches. In this context, the course you have just completed has filled the drawers of your toolbox, while the next course will use these for handling practical problems. We had the pleasure and honor of hosting you in SparseLand and showing you around. We hope that you have enjoyed this course. Stick with us to see how SparseLand is deployed to practical engineering tasks in signal and image processing. See you soon.